Hello everyone, Amy here. Today we are going to talk about something really exciting, the new frontier of large language models. A new model has been released and it is showing some incredible capabilities that challenge our previous assumptions about what these models can and cannot do. We are going to dive into a series of questions that were designed to trip up earlier models and see how this new one, the ChatGPT-5, handles them. By the end, we will have a much better understanding of what has changed and what it means for the future of AI. Let us start with a really simple test, or so it seems. It is a basic algebra problem. Earlier models, especially those from a few years back, would often struggle with simple arithmetic. They might get the first few steps right, but then make a silly mistake in the final calculation. It is like they were trying to reason but lacked a solid grounding in the numbers. This new model, however, handles it perfectly. The equation is 4.7 equal to x plus 4.13. The model correctly identifies that x is equal to 4.7 minus 4.13 and gives the answer 0.57. It even does a quick check to show that it is right. The same goes for the next problem, 5.9 equal to x plus 5.11. The answer is 0.79, perfect. What is happening here is not just a simple calculation. The model is understanding the structure of the problem, the relationship between variables and constants, and then applying a basic arithmetic function. This is a form of symbolic reasoning that has improved dramatically. The model is no longer just predicting the next token, it is performing an operation based on an underlying logical structure. This is a big step from just pattern matching on text. It is a form of grounded intelligence where the model has a reliable internal calculator. It is a foundational skill for more complex reasoning. Next, up a comparison problem. 9.56 is greater than 9.9. This is a classic test for understanding numerical values, not just their string representation. Older models might get tripped up here, sometimes confusing the number of digits with the value. But this new model instantly says false. It even gives a great, clear explanation. Since 9.56 is equal to 9 plus 0.56 and 9.9 is equal to 9 plus 0.9 and 0.56 is less than 0.9. We have 9.56 less than 9.9, not greater. This shows a strong grasp of decimal values. It is not just comparing 56 and 9, but understanding that the position of the digit matters. It is not a superficial string comparison, but a deep understanding of numerical value. Now, for a test of literal string manipulation and attentiveness. Count the number of R's in strawberry. Sounds easy, right? But older models trained on predicting the most likely next word made a lot of mistakes here. They might count the R in strawberry but miss one. This model, however, correctly identifies 3 R's. It even clarifies in a separate thought if you meant the substring R's, that is 0. This shows it is not just counting but truly understanding the query's nuance. This is also a good test for attention to detail, which is often a weakness in large models. The next one, count the number of T's in Tennessee, is another classic. The correct answer is 1. Tennessee has 1 T at the beginning, but it is full of N's, S and E's. An older model, in its haste to respond, might confuse the letters and give the wrong count. This model gets it right, 1 T. Again, it is not just about counting, but about correctly identifying the specific character being asked for. This is a testament to improved tokenization and attention mechanisms that can focus on a specific literal detail within a string. Now, let us step up the difficulty. The next puzzle is famous, the river crossing puzzle with a fox, a chicken and a bag of corn. This is the test of logical multi-step reasoning. But there is a twist. We gave the model a new rule. However, if the fox and chicken are together, they can't be left with the corn, as the fox will guard the chicken and prevent it from eating the corn. This new rule is a clever little red herring. Now let us look at the model's response. It gives the classical solution, ignoring the new rule entirely. It says to take the chicken across, come back, take the fox, bring the chicken back. This is the correct solution for the standard puzzle, where the only rules are that fox eats the chicken and chicken eats the corn. The new rule, which says the fox guards the chicken from the corn, is completely ignored. This is a subtle but critical failure. It shows that even a powerful AI can fall back on a pattern and fail to process new contradictory information. This tells us a lot about AI reasoning. While the model has a strong internal logic, it can be misled by a well-placed curved ball. A human would likely pause and try to figure out how the new rule changes the puzzle. The AI in this case appears to have recognized the problem type and applied the most probable pre-existing solution without giving enough weight to the new subtle detail. It is a failure of attentional reasoning, not just raw logic. It is a great reminder that even with these incredible advancements, we still need to be a little skeptical. Next is a physics-based reasoning problem. A ball is placed on the flat floor. An object A hits it, then B hits it. The ball rolls away from A but toward B. What happened? This is a complex test of cause and effect and understanding basic physics. Earlier models would have a hard time with this, likely giving a garbled or incorrect explanation. They lack an intuitive world model, but this new model gives a brilliant explanation. It deduces that A must have hit it from behind to push it away, and for the ball to be rolling towards B, B must have hit it from behind as well. But after the collision, B must be ahead of the ball. It is a beautifully simple, elegant, and correct solution. It shows a powerful capacity for causal reasoning and rudimentary physics engine inside its head. Okay, let us try a logic puzzle that tests for a trick. Alice, Bob, and Carol. Alice is older than Bob. Bob is younger than Carol. Alice says she is older than Carol. Then she says Carol is younger than her. Where is the contradiction? An older model might get confused by the phrasing and search for a non-existent contradiction. But this new model immediately and correctly identifies that there is no contradiction. It breaks down the statements and shows they are consistent. This demonstrates a high level of logical consistency and an ability to not be fooled by linguistic tricks. It's a hallmark of true reasoning. Finally, the water jug puzzle. I have a 5-liter jug and a 3-liter jug. I need to measure out exactly 4 liters. This is another classical multi-step planning problem, much like the river crossing puzzle. It requires tracking the state of 2 containers and planning a sequence of pours and empties to reach a specific goal state. An earlier model might fail to see a valid path or get stuck in a loop. This model, however, solves it perfectly in 6 steps. The solution is concise and correct. This is another piece of evidence pointing toward a strong internal planning and reasoning capability. It is no longer just a word predictor, it is a problem solver. So what does this all mean? The final question about the mother, sun, and candles is a great one to wrap up with. It is a simple test of common sense and a basic world model. Does the sun know the candles are lit? The model answer is perfect. Yes, once he walks in. It understands the causal relationship between a person's presence in a room and their ability to perceive things. This is the kind of common sense reasoning that was a major hurdle for earlier models. They often gave nonsensical answers because they lacked a grounded understanding of the world. The new model's ability to answer this and all the other questions correctly, from arithmetic to physics to logic, suggests a profound leap. But its failure on the river crossing puzzles twist shows us that it is still not a flawless PhD-level human. It is a model with powerful, internally consistent world model, but it can still be tripped up when we break the patterns it has learned. The real takeaway is that while these models are getting incredibly good, we still need to be a little smarter than the machine to find its limits. See you in next.